Welcome. So we're going to get started straight away because we have a packed agenda for you today. So this is the third session of a three-part bootcamp, our AI Engineering Bootcamp. And in today's session, we're going to be covering AI native engineering workflows and everything that entails. So we've got a great panel with us today. Pleased to introduce Matthias Bauer, who is Director of Software Development at Autodesk. And of course, he's also the founder and CEO of Nevasto. So hi, Matthias, welcome. We have also Ram Seetharaman, who's Head of AI and Product Manager at Synera. Hey, Ram. And we have David Heine, who is co-founder and CEO of SimScale. My name is Alex Graham. I'm a product marketer at SimScale, and I'll be here to host today's session. And so just before we get going, I'm just going to show you a quick outline of what we're going to go through today. So firstly, we're going to start off by just kicking off the session. We've got a bit of context from David. Then we're going to go straight into the presentations. We're going to hear first from Ram on agent orchestration in engineering. Next, we're going to hear from Matthias about physics AI in production. And then David is going to come back and talk about engineering and physics AI in the cloud. Then after that, we have the panel discussion, which we're all looking forward to. On that note, please do put your questions into the chat as we go along. We'll be able to bring those into the panel discussion, and we look forward to you helping us shape that agenda. So just before we go, I'm just going to quickly recap what we've heard before in the previous sessions. So if you're coming back, if you're joining us again, welcome back. If you haven't listened to one of these webinars before, welcome. You can find the recordings for the previous two webinars available on demand. But just to quickly sum those up for you, we started out in the first one talking about how to kickstart AI engineering projects, and we heard from Convion, who are a team who actually just run a pilot project. We heard about their experiences of running that project, getting acceptance and getting it started in their organization, how they really unlocked that months to hours acceleration. So it's a really interesting kind of case study. Then we also heard about why toolchain interoperability is so important. So we talked about that from the point of view of PTC and Onshape and NTOP. And then we also started to dig into how AI tools and particularly AI agents can act as a further lever for democratization of simulation, as well as, of course, being very powerful tools for automation. So we're going to take this a step further today. Just kick things off, I'm going to hand straight over to David.
Thanks, Alex. Thanks for the introduction. And I guess I want to get out of the way here and have Matthias and Ram talk in a second. But the mini context I wanted to give before is that the question really is: does the world need another webinar on AI? We think we think yes. And the reason is really, but the context of this is that I just came back from a 2 weeks customer roadshow in the US and talked with countless customers and prospects. And really, at the core of the discussion is all the time that every engineering leader today has seen their teams use, embrace, leverage AI models for to get what used to be hours of knowledge work get done in minutes or seconds. But more often than not, or actually always, it's around text. So we've seen AI has solved text. Probably it's fair to say that AI has solved code to a large extent. Maybe that's a bit of exaggeration, but it has solved a lot around code. Image generation, etc. So a lot of modalities are solved but all of these engineering leaders rightfully ask sort of, okay, like this is what I want AI to do. How can I leverage AI in my core engineering workflows? And here's like a bit of a a humorous take on this. So I want the engineering AI to do that, but at the end of the day, what it always does is like it's great for images, it's great for text, it's great for code. But it's kind of there's this gap in sort of what I want AI to do in my core engineering workflows, and then what it's actually capable of doing today. And it's not just our perception and anecdotes and across, I don't know, at this point hundreds of conversations with engineering leaders. It's also sort of proven. We ran the survey. Alex shared with me that we've shown this already in a previous webinar, so I'll keep this very short. We also ran a survey, commissioned a survey, asked more than 300 engineering leaders, and the main takeaway on their perception of AI is that there's a big gap between almost all engineering leaders. More than 90% think that AI will have a huge impact, a huge productivity boost on their engineering velocity, but less than 10%, in fact, in this case, 3% are actually seeing that impact today. And we're excited about these statistics because I would say, Matthias, Ram, would be good to hear from you as well, but I would say like 2 to 3 years ago, there was a lot of skepticism, a lot of, will this even be, will this even work? Like the hype wasn't there yet, but and we were all running already around as like preaching AI, but now the tide has changed around sort of everybody wants it, everybody sort of, wants to leverage AI, but there's like lack of clarity, a lot of dust in the air on how it actually, how is a path to production of that. And that's why, frankly, we're excited to have Ram and Matthias today, people that have put AI systems into production, deployed into production in engineering workflows. And so we're looking forward to get a bit of their wisdom, a bit of their input, more perspectives, hopefully that help everybody in the room today inform their AI strategy, their path towards adopting AI in core engineering workflows. And the last sort of piece of content I wanted to give to explain why Ram and Matthias are here today is like that everybody would like to see an AI frontier model that just out of the box, does core engineering workflows where you get a chat window and just, ask it to do core engineering work. Unfortunately, we're not there yet. But what we're excited about is that across the engineering workflow, not an Uber AI model is appearing right now that can do core engineering work, but custom, or I would say maybe a domain expert tooling that emerges at every step of the engineering workflow. So in Synera's case, maybe even sort of across the workflow that orchestrates these expert tools that are actually helpful, that are actually in production, that actually work, right? Yeah, maybe not in the fashion we would like it to have, like an Uber model, but custom tooling that's helpful along the process. And the way we think about it, this is oftentimes how we explain it to customers, is saying like across the engineering workflow, that's now like a depiction of a battery case as an example, but every engineering organization typically has some conceptual view on their product development process. And typically, if you think about this, looks very linear, very, like nice and tidy, this process, but every engineering leader knows you lose the time in the iterations. So easily, if you find a manufacturing or a costing issue downstream, this can easily have ramification upstream, and you lose weeks of time on doing work. If you go, most organizations we work with have a lead time between design generated and design evaluated, the one here in the middle, of 2 to 4 weeks. In industries where simulation pipelines are not as automated, sometimes even months of going through that loop. So just like the normal process already can take a lot of time, and that leaves out all the issues that can pop up, requirements upstream change, teams discover that they work on outdated data and they need to redo stuff, etc. So you have a lot of potential for delays, and that adds weeks of months on time to market, on shipping products. And AI systems emerge for these, for all of those tools, for all of those steps in the product development process. And we're excited to have Ram and Matthias today because we're going to cover 2 distinct ones today. And one, Ram will talk in a second about agentic AI. I don't want to talk too much about it, but the idea of orchestrating agents across the engineering process from a high level. So Ram, I'll not steal your thunder here, but across the process, and then going deeper into specifically this area here around simulation, because everybody knows you might, if a simulation runs a long time, specifically if you go through many iterations, or if you're looking at optimization, design exploration, the runtime of simulation becomes an issue. And that part, the physics AI part, is what Matthias will cover, because both of them have put these types of AI systems into production, and we're curious to hear from them learnings, lessons learned, and hopefully some hard learned lessons that the 2 of you learned and that you're sharing with the audience that they can factor into their AI strategies. With that, I'm stopping my ramble and actually hand it over to Ram here right away and make you the presenter, Ram.
Okay, thank you so much, David. I hope you can see my presentation.
Yes, that works.
Okay, great. Yeah, I think that was a great summary, David. I think you put it nicely what's happening. That's also something we see in the market with our customers. And I'm also super glad to be here to talk about what we do at Synera. And like you nicely defined, Synera is the platform, agentic platform for engineering. My name is Ram. I'm the head of AI and also product manager at Synera. I have a background in computational mechanics, so come from the simulation world, but nowadays work a lot on agentic AI and developing solution for our customers. And I would like to basically start off with where David left, and that is we all want to get, are you able to still share my screen? see my screen?
You can see it, yes.
Okay, great. One of the things we want to get out of AI in engineering is a lot of value. It could be efficiency, it could be having collaboration with other engineers, it could also be able to designing new innovative parts. But what stops that is essentially our engineering foundation layer that has a lot of tool of different data types, of different complexities spread across. Now, as we want to reach that value layer, there are different ways with AI that we can do. One of the most, let's say, quick way to do this would be to talk about AI application layer. And what we mean by AI application layer is you can take a couple of those data of different types, and you can think about from an AI mindset, is there some part of those data that I can just accelerate my processes with through AI? And that would be something like physics AI, something where Matthias can show us in a couple of moments how that works. But there's also having an AI first engineering. So moving to a platform that is purpose-built or being purpose-built for high scalability so that data can be leveraged, for example, like SimScale. And even when we have these different applications spread across on top of the raw layer, we need something like an orchestration layer that can control these different AI components, different tool components, and then make sure that the end-to-end process for your engineering processes, it's still smooth and stable. And that's exactly what we do at Synera. We try to build a platform where you can build your automation, connect to different agents, and make sure that you have an end-to-end process. Now, what is an agent? So for those of you new here, the way we define an engineering agent is something like this. Or in general, an agent is basically is a large language model powered mechanism that takes a request and it basically sends out a response. And what this means is typically we have a large language model. We also have some kind of orchestration through prompts, through context management. But also now that for that to work in engineering, we need Synera workflows. These could be rule-based automation. These could be connections to other tools. But at the end, now what happens is it's not just anymore a generic agent. It's an engineering agent. And it can get a request from an engineer, work through the LLM, the context, and the workflows, and now provide a response that's more engineering friendly and can allow these experts to interact with these tools. And that was just one agent. Now, what we try to do at Synera is to reimagine how engineers can work together with agents, and that's why we focus also on multi-agents. Now, what that would mean is we imagine an agentic organization where requirements come in. And now, instead of just one single agent, what we can have is a layer of agents that have different purposes. So on the top, we have something called these management agents. They are predominantly needed for communication, for making sure that the flow of information is goal-oriented. And then there is also the engineering agents. And these are the agents which are purpose-built for having expert knowledge in product development. And they are still in touch with the top layer that does the communication and coordination. And to these engineering agents, we give the engineering tools, the workflows. And this could be FEA workflow, it could be a PLM CAD workflow, it could also be, for example, one of the simulation workflows that you have already built with SimScale or with Navasto, and then we make it agentic ready, and then we plug it into the system. Now at the end, what we get is a solution that is autonomously generated with the right tools, with the right agents at the right intensity. Now, how do we achieve this? So what we do at Synera is, again, going back to that value pyramid, we want to start at the foundation to make sure the homework is done. And that's why the first step to going towards this architecture is to model the engineering processes in a low-code environment. And that is where we capture as much as knowledge possible in terms of workflows. And it's also very much essential that these workflows are connected to the right tools. It could be any of your CAD vendors, it could be simulation platforms, it could be other reduced order models or surrogate models, but we want to make sure that we connect to every application that you have built. And now the idea is to give this workflow as a tool via a scalable approach. And once we have this workflow now that can be shared with humans, but also with agents, then we can use these workflows to build a team of agents that can help an engineer out. So essentially, we digitalize the processes, we connect the tools, we publish those tools to be shareable, and then we give it to the agents. Now that is how a typical journey to get to a almost production-ready MAS looks like. But like David mentioned, I also want to share what we have learned along the way. One of the most common questions we get asked is, how do I know when to use what kind of AI? And I think this summarizes it well. So the way we see it is, it could be classified in terms of what is the behavior of the process that you want to, let's say, scale up, and also how much autonomy is in that process. So if it's just that the fuzziness is low and it's just a simple execution, it can be a rule-based workflow because that makes more sense. If it's one part of a bigger process where you need acceleration, where you need more enhanced capabilities, that could be an AI enhanced workflow. And then when we need more and more human-like behavior, that is when multi-agent systems really kick in. And that is also where the effects are huge, because now the processes that can be mapped with multi-agents are really high frequency, high collaborative processes, and that could serve as a real valuable asset. And one of such process is, for example, a request for code process. And what I want to show here with a short demo is how this could look like. So here we have an example for an automotive filtration system. And now looking back at the kind of multi-agent architecture, we map it in a similar way. So on the top in the orange, you see a supervisor. That's basically the coordinator agent that talks to each agent, that talks to the user and makes sure the goal is achieved. But we also have other sub-agents that are more engineering focused, and they make sure that they use the right tools, that it makes sense to give this as an output to other agents. And they all have workflows that are containing specific tools that help them do this job. So let me show an example here. So this is how the interface would look like. So it's essentially a kind of a chat interface, but you can see the complexity of the agents. You could see what agent has what tools and how are they linked to each other and so on. And now this is the system that an end user or an engineer can go and talk to when they are designing the filtration systems. So now what I can do is go to the system and start interacting with it. So I can start by asking, hey, how can you help me? And then what we see is visibility on the right-hand side. So we will see what agents were called, what did they use any tools, and what is the final response. And now let's start asking it some engineering question. So here I'm inputting a very specific engineering request with an end-to-end requirement. And now we will see on the right side what agents were called first, what was the decision that they make, and also with reasons why they made it. And we also see them using the tools. So they essentially run the engineering tools to make an engineering judgment rather than having to just guess them. And this is then communicated to the next agent. So the agents essentially talk to each other. We make sure that by having engineering tools, this communication is actually validated and verified, which is essentially one of the important requirements for having an AI-first experience, that the engineer gets to see always what's happening. So now we see the purchasing agent is making its calculation. The cost analysis agent is getting this information. And in a couple of seconds, it should also use its tool, interpret the results, and now we should get back the result in a couple of minutes. So essentially all the communication and all the tool use has been put here as a summary. So we see what are the performance parameters, what is the suitable manufacturing approach with the right context, and what is the price structure for the delivery option that was requested. Now, the interesting thing with agentic AI, it's autonomous. That means I can really ask it questions I would ask usually a group of engineers. And then I could ask something like, can you compare me codes for the system for 2 production value? And now we see the agentic system is smart enough to know that I don't need to repeat the whole process. I just need to send this information to the costing agent. So the costing agent gets the relevant information. It calculates the costs for these 2 different production volumes that I ask now. And it's going to get back with, again, a summary comparing it to the original code. So typically what we do as engineers, right? So we want to always be in context. And now we see what are the price differences. So there are all the 3 options. So that's a low volume, medium volume, and high volume part. And we see also how this has changed with respect to cost efficiency, how it has changed with respect to other insights that we need. So essentially what we did was go on a process of taking an end-to-end business process, building workflows for it, building prompts for it, orchestrating importantly with other tools, and then having a system like this to which me as an engineer, I can go and talk to. So that's what we do at Synera, and that is how you could also possibly imagine what an application or how a process with the agentic AI could look like. Back to you, Alex.
Awesome. Thanks very much. That is very cool stuff that you're showing us there. So yeah, we're going to move now on to Matthias and we'll talk about, I guess, another part of the puzzle, which is physics AI. And so if you don't already have control, you do. Awesome. Over to you.
I'm trying to share the screen. Do you see it?
Yep, we do, yep.
Okay, so thanks everyone. Also, thanks for having me. Thanks, Ram, for this super interesting thing on agentic workflows. I'm gonna touch on a different aspect, which is physics AI, and how we labeled this almost a decade ago is AI accelerated design and engineering. So this is going to be more about the relevance of the use cases and the relevance of integration than about the underlying technology. So I'm Matthias. I'm doing this for more than a decade now. I'm an engineer by training. Founded Navasto over a decade ago now. And what we've developed is a software toolkit that allows to make real-time predictions based on geometric inputs that show you something similar to what you would get from a first principle-based simulation. And touching back to what David has talked about a moment ago, this idea of everyone tries AI, but a lot of people see issues in the return, in the value, is something that's almost funny coming after 11 years of working in this field, because when we started, no one really believed that AI could actually predict physics. And then ChatGPT happened, and suddenly people believed that would be a magic bullet. And now we are getting the headlines that I'm sharing at the moment. So whatever you Google, you hear a lot of people are seeing failed POCs. So the question could come up if this is all hype and there's actually no value behind that. And I guess, you know, that's a rhetorical question coming from me, or otherwise I wouldn't be sitting here. So the answer to that is definitely no. It's not hype. It's a lot of value in there, but the value comes from the right choice of the use case and the integration into the workflow. So just talking quickly about what physics AI means, what we're doing. In essence, we are showing a geometric deep learning model or another machine learning model, variations of geometries, so inputs that you'd use to run a simulation or experiment, and the result that comes out of this first principle based simulation. And not only one, but a combination of that, and that's the training process. So a lot of different variations that are in there, and a lot of results that are, well, coming from the first principle based solver. So that we can then, in the second step, query the deep learning model. I'm sorry, are you seeing the right thing here? This is
we're seeing the car geometries. Yes, design 1, design 2.
Sorry, this is so that in the second step we can then run an inference and get a real-time answer for a new and unseen geometry. So this is the underlying idea of physics AI. You train a model to understand what the impact of geometry and boundary conditions is on your physical results. So if you showed a new geometry and a new boundary condition, you get that answer back more quickly. And one of the common ways of presenting the results of such a physics AI model is what you see on the screen now. So it's a comparison between a simulation result and an AI prediction. And the bottom line here is they're very close to each other. They're more or less the same. The simulation takes a long time and the AI prediction is super fast. So this is what physics AI does. That's not necessarily how you should use physics AI, because the very first question that I get for a decade in probably hundreds or thousands of conversations is, how many samples do I need to train a model that gives me an accurate prediction? And this is a very valid question, but it's also the completely wrong question. The actual question that one should ask when starting about thinking applying physics AI in a workflow is about the use case. So what's the biggest pain point I have where I see that AI could actually make a dent into my problem, actually create value without throwing everything out of the window? So the use case is the one thing that's super relevant when considering using physics AI. But a lot of people at least think about the use case. The second thing that almost everyone starts to forget in the beginning is the aspect of integration. And to illustrate that, I just picked a very old example from another technology that was new, like 120 years ago, and that promised a lot of efficiency in the manufacturing. So when electricity was introduced to manufacturing about 120 years ago, they started to replace the steam engines that drove entire factories with electric engines and expected efficiency gains. However, that doesn't happen. That didn't happen back then. And people were wondering why. And the thing that's now obvious looking back at the situation 120 years ago, but was absolutely not obvious back then, was they just replaced one thing with a cooler, newer thing, but they actually didn't really address the problem that they could fix with that. So steam engines drove factories with a big shaft, and the torque was distributed across the factory with a belt system. And if one of the belts broke down, they had to stop the entire factory. And whether you do that with a steam engine or an electric engine does not have any impact. So the problem is not necessarily the source of the power. Switching it out with the new technologies doesn't solve the problem. You need to think a step further and think what you can actually do in terms of the organization of the work and the workflow to make a dent there. So what did they do? Once they figured out that they could route electricity to different machines and put a smaller electric motor there, this is where the actual efficiency gains came into play, and people could start to organize their work differently. So the two things, use case and integrations, are the things that I've learned over the past decade that make the difference between successful implementation of physics AI and a failed POC. So what's physics AI useful then? What's a new thing you can do? It's obviously not a magic bullet, but what it can do is it allows to left shift and to democratize physics-based insights. So you can get people insights into the physical performance of a product that didn't have it before, and you can also give it to more people that either couldn't have it because it was just too expensive to run a simulation, or because it's an expert tool and they weren't trained to use it. What it's definitely not is a substitute for a CFD solver, any first principle-based solver for that matter, and any physics AI implementation that aims at replacing a solver are the ones that are prone to fail. So with that, I'd like to show you a successful use case and the integration. So a very concrete problem in the automotive industry is the design cycle between designers and engineers. So a designer working on a car exterior, for example, commits a change to a geometry, which takes a few seconds or a few minutes, and then they need to understand how this design change has impacted the KPIs, like the range of a vehicle, the drag coefficient, or the lift forces on the different axes. And this is something that they learn from simulation. And the main issue there is that they need to hand over the geometry to someone who cleans that geometry, then to the engineers that run the simulations and give them back the result. And this is a process that takes, depending on the OEM, something between a few days and a few weeks, actually. And if you give a designer the tool to make this prediction in real time, so to query a deep learning model, to understand what the geometry change had an impact in terms of physics, they can actually iterate on their own or work together with the engineering colleagues in real time and solve problems much more quickly. So the underlying idea of leveraging physics AI in such a context is that they can work together as teams and solve problems like, could I change something like that, within minutes instead of going back and forth over a few weeks. And this is how this looks in practice. So the second aspect here is the integration. Designers across all OEMs, it's like 100% market share there, use the tool Alias to do the designs and their A-class surfacing. So everyone is using this tool, and within this tool, they can now access a deep learning model. They just click a button, they get back the performance predicted by the AI model, and then they can go immediately back to their tool set that they're currently using to do the design modifications. They can do larger changes, smaller changes. So their actual workflow doesn't change at all. They can do all the same things that they did before. And then when they want to know if the design change went in the right direction or the wrong direction, they can simply again query the AI model and get the prediction back in real time. And this is a use case that cuts off weeks of automotive design studios development times, and thus something that actually validates putting a lot of effort in those AI models. So use case is incredibly important. The second thing is integration, as just mentioned. So we're also very proud that technology is integrated with Synera, for example, to access all those different CAE tools that are used to generate data for model training, and also for SimScale, which has really a unique use case, fully integrated model training that then exposes the AI model to iterate fast, side by side with a first principle based solver. So going back to these original questions, how many samples do I need to train an accurate model? Now, depending on the use case, once you have defined the use case, you can actually start to look at an answer to that. And depending on what you want to do, that could be 25 or 43 or 250 if you want to do a size and proportion studies. Or if you think about the design studios of OEMs, they regularly put 2,500 simulations in there. And looking at Formula One teams, they are feeding models with tens of thousands of geometries. But the answer to this question at the end of the day should better be that the amount of samples that you need to train an AI model is reasonable to justify the gains and the investment. And if the answer is not that, then you probably have picked the wrong use case. With that, gonna hand back.
Thank you, Matthias. That was great, and yeah, you answered lots of the questions that we often get about physics AI. So thank you very much. All right, so next up we have David. He's going to add some final food for thought before we move on to the panel discussion. So yeah, over to you, David.
Yeah, I have not a lot to add, other than clearly we all hope that Matthias will share when this car will be available for purchase. That was designed to it because that looked very sporty, so that looked good.
Really?
I mean,
it is a terrible drag coefficient. The designer did it. No engineer was actually involved.
I think the aesthetics look great. But clearly, I mean, the fact that we have Matthias here is that we very much have a shared vision around that. SimScale integrates both with Synera and Navasto, now Autodesk. And we very much believe in, or not just believe, but we see in production to have sort of agentic AI do automate and reason and perceive through engineering workflows that were previously hard to automate. And then on the other side, as you explore design spaces and you narrow in that a physics AI model to then evaluate much faster a design space. Like, we're so sort of bought into that, share that vision, and clearly, I mean, the fact that Ron said it nicely earlier. So at SimScale, we integrate all of this vertically in an attempt to sort of make it much more easier, accessible to everybody, and make it broader available. And so really, the two things in action. That's why like a 3-minute contribution from our end would be just a small demo. We recently put together, and it's a server model. And we can see, because we've seen a car example and an automotive filter example. So here, one from electronics. I guess these days the AI boom is driving a ton of demand up, down the data center build out supply chain, and so that would be sort of a server rack. You have compute units in there, and the typical engineering challenge, you have some heat that needs to be dissipated, you have a bunch of heat sinks, you have fan placements. And so again, typical challenge of sort of now saying, okay, like now you want to validate with respect to the thermal performance. So how do you do that? And what we heard earlier, and I guess bringing that point home, Matthias said the automotive OEM takes days to weeks to turn around from a design generated to design evaluated. Depending on the industry, we see in aerospace like 4 weeks, automotive maybe 2 weeks. In industries where simulation pipelines, where product portfolios are broad and simulation pipelines are less standardized, we sometimes see even months to go from a generated to a design evaluated. Again, to be clear, there's of course in every organization there's high prior simulation projects, and they get very fast. They get done the same day. But in average, as a rate limiting factor for design iterations, we're typically talking weeks. And each time we look at why does it take weeks? Where's the time lost? Yes, part of it is in the actual solve time. We've seen Matthias talk about. Part of it is in the actual wait time until somebody else picks it up. And we heard from Ram talk about the agents being able to pick up work, agents that don't sleep, agents that autonomously can pick up work if they've been instructed to do so. And so on our side, we're calling these two systems engineering AI and physics AI. And I think we've seen, Matthias talk about how Navasto and Autodesk do this broadly for, solver independent and in a broad way. And then Ram talked about how Synera is very much sort of almost like tool agnostic, right? That you can use. So with SimScale, we vertically integrate all of this such that it works out of the box. And like now seeing this in action is this that's just a 3-minute sort of visualization of that, sort of our implementation of that. So we can see now in sort of as a first step, like it would take me a long time to wait for my simulation expert to get back to me to run that simulation. And instead, I'm choosing to serve a CFD agent inside SimScale that has previously received instructions on how my organization does thermal management studies of server racks. It has seen example simulations of other CAD models. And then now we can see it here on the right. It's a smart automation that now can see the CAD model, that sees the context, that sees the instructions, that sees example simulations. And we can see now, if we would do this live, we typically do like that, right? So we take our hands up, and so now the AI agent reasons through it. It's fairly fast now, but you can, if you've used SimScale before, you can see it on the left, and now it goes through material reasoning. So it has seen and previously executed simulations, like what material we typically use for the heat sinks. Is that a part name that I've seen before, where I can assign a material that has been used to? Is there a component that I know or that I've been instructed to assign? Next, we can see boundary conditions. It shows a natural convection inlet outlet for the flow domain, and now it eventually would go through. It eventually goes through the advanced concepts. So in this case, we're looking at the power source of the two compute units and a bunch of chips. Also here, what type of wattage do we have? Have I seen this component before? It would eventually go through a porous media and then the fan models. An important bit here is like human agent collaboration, because what we're looking at is a GUI, like the agent in the GUI. We call this a workbench agent. So I can work side by side with that agent, which is an important modality, because in this simulation, the agent actually stumbles when setting up the fan curve. So the agent can invoke the human and say, hey, look, here's at this point, like we need to define a fan curve, but I lack data, or I lack sort of the capability to do that. Can you help? So you can see it here. The human goes in, the human, in this case, I think it was Steve. So, let's refer to Steve as human. Steve, the human, went in, like put it in, said, okay, we're done. And now sort of the agent is done and can run the simulation, right? And this would now take an hour, 45 minutes to complete an MOS boundary study. So that ran a normal finite volume solve here, but I could cut out the wait time to then run the normal finite volume solve. Now the logical next step is what Matthias talked about. So we're seeing now a NAVPAC in action integrated in SimScale, where based on similar server configurations, now a physics AI model has been trained. So you see the user here invokes the one-use server AI model, and we can see a near real-time prediction of the results. And if you watch closely in the lower right, it says scalar result predictions. What I'm actually interested in is the temperature monitor on the chips, right? So a scalar outcome. And you can see now I'm assigning a new geometry, again unseen, and I immediately sort of everything is topologically mapped, and I see a real-time prediction again of the result field and the temperature monitor. And then the last bit naturally is, okay, now you want to let the agent loose with the physics AI, and then you can explore now optimization things. Now it gets wild here. We can see an agentic optimizations that rips through design changes. You can then couple it to, if you couple it to a parametric model. So you suddenly, what we sometimes say is, if you have the ability to now automate the parts of choosing the next design iteration and then being able to within seconds evaluate that design iterations, sort of design spaces suddenly become, you can search much deeper, you can broader. And so that's sort of almost like what Ram explained around agentic AI, or Matthias explained about physics AI. We implemented that inside SimScale, but clearly in collaboration with Synera, there's broader workflows that are possible. The technology Matthias showed sort of clearly works outside of SimScale, so that's why we're excited to have them here today and share a bit their insights. Good, but with that, it's almost like just our small contribution of how that looks inside SimScale. With that, Alex, I would hand it over back to you and stop sharing here.
All right, thank you, David. Let's see, I'll just pop up. Oh, I didn't mean to do that. I wanted to show you that. Does it work?
Yes.
Awesome. Okay, so on to the round table. So we've got lots of things I think to talk about. We've had some questions from the audience as well. So I had a few questions just prepared here, which I'm just going to kind of use as a bit of a framework for this discussion. But also, as I said, we've got some that have come in, which I think also align quite nicely with these actually. So we're going to stick with this one first. So talking about trust, and I think this is something that there are things to talk about both in the physics AI side and in the engineering and agentic AI side as well. So maybe, seeing as we've just been talking about physics AI, shall we start there? And I'm just going to sort of augment this question a little bit with some input we had from the audience. So somebody was asking about how, when you're training models, do you just need to train on representative geometries, or is it enough to train on physics? And I suppose this is kind of a question about generalization of those physics IO models. Yeah, so over to you, Matthias. Do you have any initial reaction?
Yeah, absolutely. I mean, what we have done and what we've seen successfully implemented is data-driven, meaning we train on relevant geometries and relevant boundary conditions. And relevant in that case means something that will be similar to what you're going to see in your use case afterwards. So you cannot, at least to my knowledge, actually train a neural network to understand physics in general and then use it as a first principle based solver, or as something as general as a first principle based solver. So there are those ideas of physics informed neural networks. They were around for a very long time. There was the proper general decomposition like 8 years ago, which was a bit of a hype. So all the things that had real physics somewhere, either in the base functions or in the loss functions, are interesting, but they are not used and not useful in practice, at least not at the scale that I've seen implemented. And for a very simple reason, it just takes too long to train and it's too complex. And at the end of the day, you still will only train a model and not really solve the actual differential equations. So for everything that's useful as of 2025, those are data-driven methods. Methods to develop, they go from things that were not really great at generalizing like 6-7 years ago to something that better generalized with GNNs. There are new architectures coming out there. So the cool kids all play with transformers at the moment. They show the tendency to better generalize, but it's still all based on variations of geometric input. None of those models truly learn physics.
Sure, yeah. So it's hard to get your dent in the process. Yeah, a related question maybe. So when you're using an AI surrogate model, under what circumstances would it give you the wrong predictions? And I guess how would you know?
Yeah.
How do you tell?
Uncertainty quantification. Uncertainty quantification is the holy grail of machine learning in general. So there is no analytical way of estimating even the error or even the error band of any given machine learning or at least any deep learning model. To my knowledge, but I haven't heard anything over the past decade. I think that's a fact. So what we need to do when we deploy it in practice is we need to work around it. There are ways, statistical means, I mean, it's data driven, it's all statistics. So we leverage statistical means to not only give a prediction, but also a variance of these predictions. And then people start to learn to interpret what the variance of a prediction means. There are other ways. For example, we check the similarity of an input to what the model has seen during training automatically. We use, in general, different forms of model architectures combined to also identify the regions that have high uncertainty on a prediction. So bottom line here is there's a lot of different methods that we expose to the end user and eventually also collect and combine back so that we can show a designer something like a green light for a trusted prediction and a red light for do not trust a prediction. But it's at the end of the day a best practice provided by us, by the method development department of OEMs, that collects statistical information on the inference that allows you, based on experience, to judge whether to trust a prediction or not.
Got it. So yeah, about knowing what your tool is supposed to be able to do and sort of where to use it. That knowledge sounds important. And yeah, thinking about this from the agentic side, Ram, we had a question about how do I, how do you understand like when something becomes a problem or when there's a problem encountered in one of those agentic workflows? So we saw that you had the trace of like what the conversation was. So yeah, how do you spot errors in that process and what do you do about them?
Yeah, absolutely. I think trust is also a very complex layer of things. So it like one aspect of it is absolutely the technology, like Matthias explained. Uncertainty quantification is for any model, as far as I know, still a big challenge. So that is also for LLMs. So there are certain aspects when we build an agent that can be led deterministic, that cannot be deterministic. For example, a reasoning. Why will an agent pick aluminium instead of steel? This needs to be validated in some way, but there are some aspects that should be extremely simple. For example, should it use a linear simulation given a temperature range, or should it run a static simulation for load? These kind of deterministic steps can be easily verified. So a lot of it definitely boils down to who needs to trust these. Is it the engineer who builds these models or agents, or is it also the engineer who would perhaps use these models? So for example, what we do with agents is we want agents to work with many engineers, but the one that probably builds is just one person. So there are different ways how you can give trust to the engineer who actually builds them and work a lot on, let's say, how the product feels and how does it communicate to the end user so that it feels it's more trustable. That is something we work on. So we try to keep it as much as visible as possible. Of course, not on a more, let's say, architectural level, but why does an agent take the decision to use this tool? Probably there is a reason that it says, I looked at the geometry, it looks like a slender geometry, I need to use this. Having these kind of reasoning visibility is also very helpful for agents. And that is how I think we can give different trust levels to different end users or engineers.
And can you have a conversation back with your with the agent? I guess you're talking to the head agent in your agentic team.
Yeah.
And how are those agents communicating with each other? Are they communicating in the way that we would communicate with them, or do they have their own way to speak to each other?
Oh no, they for now they can speak every language. We as humans can also speak, but also interesting. Sometimes some of our customers have global regions everywhere. So the end user sometimes tries to chalk in, for example, Spanish, but then the engineer who created the agent would have put the information in English. So there is, of course, a certain loss in terms of words and knowledge. But predominantly what they do is capture the current state that they are in. So probably, let's say if I was an FEA agent and I need to talk to a cloud agent that does CFD simulation. So the FEA agent would wrap up its work. Hey, I got this geometry. These were the tools I used. I got these results. But to respond to this code or to finish this design, you have to help me with validating if the CFD simulation looks good. So it's basically a handoff of current statement of work to another agent. So it's a summary of between agents.
And the small addition, Alex, I would say, because I agree with Ram, right? There's a lot of like that there's technology that can address that issue, or technical aspects that can address this issue. But partially, oftentimes, I was in a lot of conversations where I simply said, I think the analogy to a junior engineer is oftentimes also helpful. So sometimes you just should not trust from the point of view is that, and that's why, from my point of view, traceability and auditability comes into mind. So whatever, you know, agentic systems like need to be like for production use. I mean, it also informs a lot of our architecture. Sort of like whatever the agent has done, you need to be able to review what has it done, right? And that's why we've seen sort of in SimScale that you can inspect the setup, the collaboration with the agent is key to see, okay, where did it get stuck, that you can actually see what the agent has done. From my point of view is, you know, and that's, you know, traceability, auditability, versioning is key. And it still doesn't mean like, you know, there's a lot of junior engineers working in a lot of organizations that are doing meaningful work, right? Because of course that eventually has to be, you know, reviewed by a senior engineer eventually, or like in a design review, but there's still like meaningful work that can be done this way for sure.
All right, let's move on to our next question, because I'm aware of the shortness of time, so it'd be good to get through a few different angles here. So yeah, this is an interesting one, I think. How do you balance like the need to automate with the need to maintain kind of engineers' eyes on problems and keep your engineers actually working and making engineering judgments? Yeah, like Ram, how does that look from Synera's point of view? Because you're looking to automate lots of processes and get them kind of to give them entirely away to another system.
Yeah, absolutely. I think it's also a very good question, because it's also relating to empathy. We as companies kind of have to develop in designing these AI solutions. I think the simplest principle is if you're clicking multiple buttons and that buttons have not much thought process behind, absolutely go for automation in the first place. For example, it could be just copying data from one software and just putting it into different fields of another software. This is something that's super critical, that it can be automated and there is no engineering judgment involved. In terms of automating, for example, should an A pillar have these ribs, or should it have ribs that look like that? That is where also what David mentioned, that this expertise probably comes through years of experience. We often talk to engineers who can just look at a design, they do some kind of surrogate modeling in their head, and then they know, oh no, that rib shouldn't look there. And that's something I think we have to learn to appreciate, that they have these patterns recognized in their experience. So what would be a great mechanism is we automate all that we can and still try to include having the expertise from engineers in this loop, rather than having to separate that an AI system just does the automation and then what the engineer does is separate. But if we can think about use cases that where both of them need to coexist, I think that is how we could balance, in my perspective.
Matthias, and you've been obviously accelerating simulation massively using physics AI, you're going from sort of maybe hours or days down to seconds for physics predictions. But do you also see like an increasing need to combine that with the kind of like agentic workflows that Ram is describing to, I guess, make sense of that data and sort of serve it to engineers?
So within Autodesk, obviously, yes, a lot of efforts are underway to use agentic workflows. For NavPack and the customers we work with specifically, we don't really see the need or the interest of the engineers for that thing specifically. This is a very simple reason. A lot of the things are not allowed to be flexible at all. So people develop a best practice, like an automotive OEM wants a certain way of training an AI model, wants a certain way of running a CFD simulation, and that's hard coded. So even if 100 people are using the simulation tool, a group of people has defined how to use it, and then people are not allowed to change that. So there's much less interaction in terms of stuff that you can actually automate, because you want consistent results across large teams, and the use case is more or less always the same. So we want to run a simulation of the external aerodynamics of a vehicle. So there's less need for agentic workflows of that kind. But we do see a lot of relevance, of course, in other aspects. Complex tool usage, for example, like Alias is a tool that's used by a lot of people with very different tasks, and there are steps in there that are, as Ramesh just said, combining a lot of clicks and buttons. So this is where agentic AI absolutely makes sense.
Yeah, so like eliminating kind of busy work and meaning people can get started with tools more easily and learn. You don't have to learn user interfaces and that kind of thing.
Absolutely. And I think the most difficult part there is really not to take away the creativity. I think that's true in engineering, but it's even more important in the design studio, for example. So if you would automate something that automates in essence too much, you would kind of end up always the same thing, and you want the human to be able to go in the wrong direction. So this is something that I've also learned more or less recently when talking to more and more design studios. You don't actually want to automate everything. You want to automate the tedious parts.
Got it.
And I think, Alex, just also looking at the time, because I also looked, because we're probably not going to go through all, get through all questions, but I think there was one interesting question around how much time this is, because we kept on mentioning automation. And I think because physics AI, Matthias showed this nice 7 hours to a couple of seconds. In agentic AI, I think, Ram, I'm not sure what your experience is, but oftentimes I feel like even automation doesn't do it so much justice, because automation oftentimes means, you know, you get somewhere 5% efficiency or 7% efficiency gains or something, which is typically doesn't make a big difference. But from our experience in production, it's because some tasks would lie around for 2 weeks somewhere in the backlog, and it would have not been picked up. So sometimes the time savings are multiple orders of magnitude faster, not because like that, you know, like the agent is so much faster, but the agent can work when stuff would sit in a backlog. And so that's why it's hard to sort of, you know, provide an equivalent time saving for this, because it impacts it on a process or organizational level. And that's why the main impact is not so much that you saved a bit of time here or a bit of time there. The main impact is rather, oh, suddenly like I can explore hundreds of design versions where I could previously explore 1 in 2 weeks. And so that's why I almost feel like automation is sometimes doesn't do the concept of agentic AI justice, because it eliminates all wait times. I'm not sure, Ram, if you had additional thoughts on it.
Absolutely. I think it's definitely going to be also referring to Matthias' point, always stemming from a use case perspective. So it also depends from organization. There are 2 ways to speed up processes. So either we make people work more closely in a more smoother fashion, that they are not blocked by communication, or there can be just certain simulation that are the biggest bottlenecks. So picking the right, let's say, solution would be important. So if an organization already has a lot of communication channel, they try to smoothen out communication as much as possible, but they don't look at the simulation bottlenecks, then that's probably agentic AI is not going to have so much effect. And also in the same way, if they start with just gathering data, but don't do let's say a process orchestration, and that's going to be not so much in return of investment. So I think I would totally agree with Matthias' points. It definitely depends on where is the biggest pain point today. Is it on the tool layer? Is it on the process layer? And then looking at it from these kind of angles.
Lovely. All right. I think we are out of time. But thank you very much to all of our presenters for today's fascinating presentations and discussions. And thanks very much to the audience for joining us. Hope you've enjoyed these 3 sessions. And of course, you can get the on-demand video recordings in your inbox very shortly. Yeah, so all that remains to be said is goodbye. See you next time.
Thank you, everyone.
Thanks, everyone. Bye.